Am I on the right? Okay, yeah. Yeah, thanks. I'm Lauritz. I work at Bispebjerg Hospital in Copenhagen, and I'm working on this new technique to diagnose and delineate skin cancer. So, laser surgery. Lasers are not used for high-risk tumors, and that's because they ablate the tissue. So, really what we want if we want to treat high-risk tumors is to know what did we ablate. And so ablation is really good because it enables us to do the surgery, but we cannot really detect what was in the ablated tissue. So this is AI-generated image of a surgeon that's blindfolded, and really what we want to do is take the blindfolds off of this guy. So we are developing this for keratinocyte cancer. And if you're a clinician, you might see this and recognize it as keratinocyte cancer. If you're a pathologist, you might see this and recognize it. But if you're an analytical chemist like me, you wonder, how does it look on a molecular level? And we don't really know, but we're going to find out. So this is a mass spectrum. Can I just see a show of hands how many people know mass spectrometry? Okay, a few people. So I'll just really quickly go through mass spec. And the idea is that we have this molecules, molecular mass on the x-axis and the intensity on the y-axis. So we can have a lot of different molecules measured by intensity. So this brings us thousands of data points, all saying something about the sampled tissue. If we do this in 2 dimensions on a skin section like this, we can get what is called mass spec imaging. And this is usually done with a very focused laser, so we can get down to 5 microns in resolution. So mass spec imaging is this 2-dimension array of mass spectra, and this is a lot of data because we can have upwards of 100,000 pixels per mass spec image. And the really cool thing about mass spec image is that we can zoom in on a specific metabolite. So if we take the mass 885 here, we can see that it represents the tissue from this SCC mouse model. We can then shift the mass and say if we want to look at where's cholesterol in this sample, we can focus on the distribution of cholesterol here. But what if we want to know where is the cancer? We don't really have a molecular mass specifying the cancer, so we need to do something else here. And that's where machine learning comes into play, because we do have a lot of data. So if we create this extraction mask based on histology, we can extract spectra from the mass spec image that represents each class, and in this case, non-tumor versus tumor. So we have these representative spectra and train a machine learning model based on that. And here we can see that our trained model is able to predict the tumor area quite well. And if we really do this on a larger scale, we see a representation of the classification here. And when we then ask a pathologist to evaluate, did we actually diagnose the cancer and delineate the cancer, we see a quite nice correlation or alignment with histopathology here, so almost perfect alignment with histopathology. So this is in BCC and SCC models on mice. But now we can do this on a sample slide, but we really want to do it in the clinic. So we want to do it based on a surgical laser. So the idea is that we have this tissue, and we ablate some of the tissue with a laser. It produces a plume. We suck that into the mass spec, generate a mass spectrum, evaluate that through our machine learning model, and predict whether it's healthy or cancer tissue. And so as soon as we hit the tumor, we should know that it's tumor tissue, and preferably which class of tumor. So this is what that looks like in real life in Copenhagen. This is our setup. So can you see any? No. Okay, so in the back there you have the surgical laser, and right now it's mounted to a stage where we have imaging set up. But you can take off the handpiece and just use it as a diagnostic tool. To the left you see the mass spectrometer, and to the right, the computer that is running the machine learning algorithm. And so right now we are doing this on bulk tissue, and we're going to show that we can actually remove a tumor with a specific margin based on this technique. And the next thing is going into the model and see, can we get a molecular profile of each tumor? And of course, at some point, take the blindfolds off of this guy. Thanks.